in section 410 with something called modeling with circular functions. Now we've done modeling with quadratic functions back in chapter 2 and exponential functions and linear functions. We did all that back in chapter 2. We would take a set of data and we would see if it fit one of those patterns. Well, you're pretty much going to do the exact same thing here with section 410, but this time we're looking at modeling something that creates a cycle over and over again, like a sine wave or a cosine wave. Example 1, which is pretty much at the beginning of the section, talks about an oscillating spring. And if you look at the book on page 293, you'll see that as the spring goes down 3 centimeters below the point of equilibrium, get that in there. You'll see that it's coming down 3, and then when you release the spring, it goes up to this point of equilibrium, goes above the point of equilibrium, back down, and then back down below, creating almost a sine wave. And so we can take the data that we're given. They would give us some type of data, such as time. This would be our time, our x value, 0, 1, 2, 3, 4 seconds. And they would say, okay, you're 3 centimeters below the point of equilibrium, and then you're at it, and you're 3 centimeters above, and then you're back to it, and then down, completing one particular cycle of that particular function. And so we can then graph the data. So the first thing we do is take a look at the graph. Obviously 3 is the high point and negative 3 is the low point. 1, 2, 3, 4. And at 0 we're down here, and at 1 second we're at the point of equilibrium above and then back down. Okay, so we can think of this as the data which creates the sine wave. Okay, and so then we can start asking ourselves, well, could we come up with an equation for that? So the second part of it would be to write an equation. Well, and specifically, let's do a sine function. We'd have to make a decision whether we wanted a sine or a cosine, because that's going to determine where h and k are. K obviously would stay the same, but h, that's the big deal, is where would you find h? Now, since we can clearly see that the period is equal to 4 seconds, and we know from what we've talked about in class that that is 2 pi times a, then we can use our skills in algebra to find the value of a. In this case, a would then be 4 over 2 pi, which would reduce to 2 over 1 pi. So there we have our, all right, next we need to find our amplitude. Our amplitude is found by taking the difference in the max and the min and dividing by 2. So if we take the difference between the max and the min, you've got 3 plus, 3 plus negative 3. Oops, sorry, I can't even follow my own notes. Subtracting them and then finding out 6 over 2 is 3, there's your amplitude. Now I know that you can all count from the picture and you can clearly see that it was 3 from the beginning. You didn't need me to tell you that. But the thing is, once we get into more difficult situations where we have just a set of data, and yes, you will be using your graphing calculators eventually here, you're going to need to know that it's the max minus the min cut in half. So that's and we all know that that is the value of b. Next we need to find the value of k. K is the average of the max and min. So max plus min over 2. In this case that would be 3 plus, why do I keep writing plus or minus? Plus negative 3 all over 2. Yes, it's an off day. I've been teaching too long today. Anyway, you find your k value is 0, which we could all tell. If you look back at the picture, you can see that the center line, the point of equilibrium, is what they call k, and that equals 0. Well, the last thing we need to find is h, okay? And that has everything to do with this sine wave. We have decided to use a sine function because that's what they've asked for. And so we know that hk sits on the center line, on the curve, on the way up. That would be this location right here. If it were a cosine function, we would pick the point that's underneath the maximum. But this right here is our HK. Now what is that point? That is the point 1, 0. So H must be 1 because we chose a sine wave. Well, now we have all of our pieces of the puzzle. We know that it's y minus k over b equals sine of x minus h over a. So all I'm going to do is I'm going to put all my pieces of the puzzle together. Y minus 0 over b, which is 3, equals sine of x minus, what's h again, 1, all over a, which was 2 over pi. And a lot of times we set these equations equal to y, so a little simplification doesn't hurt anybody. I know, you're going to complain to me. Anyway, there you go. There's your final equation that you got. Now, truthfully, either one of these is okay, but this one is set equal to y, which is what we do a lot of times in these examples, is set our equations equal to y. The next thing we need to do is go to example 2, which is in our textbook, and that is on the satellite. And if you look on page 295, you're going to see that the satellite is orbiting the Earth, and it goes a maximum of 4,500 kilometers north of the equator and 4,500 kilometers south of the equator. And in so doing, over a period of time, it makes a cycle going back and forth across the equator. And so it's doing this every 2 hours. It tells us in there that the complete rotation happens in 2 hours. They do describe north of the equator to be positive and south of the equator to be negative. So that's where we're getting this idea of a plus and a minus. The equator obviously being the center line of our graph. But they say that 15 minutes after launch, it reaches the maximum of 4,500 kilometers north. Okay, so that's positive 4,500. Well, there's a data point right there. 15 minutes, 4,500 kilometers. Okay, then it says half an orbit later. Half an orbit later, that would mean it was at the other side, at 4,500 south. That's the way they describe it. Half an orbit later. Then it's 4,500 kilometers south. So you got to think a little bit about that one. They do tell me that it takes the orbit, which in our case is the period of the function, takes 2 hours, which would be the equivalent of what? Equivalent of 120 minutes. What is half of that time? Well, 120 divided by 2 gives me 60 minutes. That means when this says half an orbit really amounts to this 60 minutes of time. So 60 plus 15 makes 75, and we're 4,500 south, so negative 4,500 at that particular time. So if you start thinking about this, if you were to look at a graph and think about 4,500 kilometers north and 4,500 kilometers south of the equator, and we'll go in increments of 15, because that'll fit with what we're doing. We've got at 15 minutes, we're at 4,500, and at half and 75 minutes, we are at negative 4,500. You know that the distance between here and where it's going to start to repeat the pattern has to be 120 minutes because that's 2 hours, right? And so that would occur at that 135-minute time period. And so halfway in between these two, same routine we've done before, okay, with this wave. And so we can look at this particular cosine wave. So they can ask me questions like, okay, find an equation using the cosine function which models the distance. So if we talk about cosine, this point right here is going to be my h and k. Well, that's the point 15, comma 0. So we've got our h and we've got our k. Obviously the distance from the max to the center line, which is your amplitude, equals 4,500. And yes, we could have, found the average or taken the distance between the max and the min and divided by 2. So that's another way to look at that. Like we talked about before, the distance between the max and the min, and cut that in half, we're still getting 4,500. And like I said, this example is easy. If we do one, we'll do one in class, especially from the homework, questions 9 and 10, where you're going to have to use the max and the min to find that amplitude. It's not just going to be so obvious. We already know from that then that this is the value of B. We've already got our h at 15 and our k at 0. So what we really need is A. That comes from the period. Well, we know the period is 120 minutes. Okay, since h is in minutes, we'll definitely use the period in minutes, and that's 2 pi times A. Simply solving that by dividing by 2 pi gives me an A value of 60 over 1 pi. 60 over 1 pi. So now I have all the pieces of the puzzle, all right? And I can go ahead and put y minus k over b equals cosine of x minus h over a. Well, there it is. Now we can put it in the y equals friendly form, right? Y equals 4,500 cosine x minus 15 over 60 over pi. And there's your equation. You will notice if you take a look at the problems on page 297, questions 9 and questions 10, which we'll talk about in class, that they're doing a little bit more. They're taking a set of data and they are doing all the different things. In fact, in question 9, you're going to have to break out your graphing calculator. We'll do that in class. I know that's kind of unheard of in chapter 4, but you'll have to make sure that you have it in class so that we can work on those problems together, especially 9 and 10. Question 10 we'll definitely do in days, so we'll make sure that we convert those dates into days of the year. And then we can graph that out using list 1 and list 2 and all that good stuff we haven't used in a while. So I will talk with you soon. Make sure you go to the SurveyMonkey and evaluate examples 1 and 2 based on how comfortable you feel with them. Thank you. Talk to you soon. Bye.